to compute the volts. So let's continue with the full scale converter control system, okay? So let's analyze the following, the full scale converter control system. And this is the control system. So I will have here a full scale converter wind turbine generator. In this case, I will have the reference frame SVRT. This is the stator voltage reference frame. And besides, I will have here the rotor reference frame and the synchronous reference frame. In other words, I will have this is the synchronous reference frame. Okay, I will have here the stator reference frame and the rotor reference frame. Normally, it's possible to use this notation. Okay, it's possible to use this notation. Okay, so let's analyze this block diagram. So due to the decoupling control of the converter, the wind turbine generator and the grid are completely decoupled. So I will have here the control system is splitting out in the wind turbine control, okay, and the converter control. This is the full-scale converter control system. So I will have two types of control. Okay, the control system of this turbine comprises the wind turbine control system and the converter control system. So what is the objective of this control? And what is the objective of this control? So let's analyze the first one. Okay, so the wind turbine control has the following objective. The first one is to control the active power of the generator. Okay, to control the active power on the generator, and the second one is to track the optimal operating point of the wind turbine. Okay, so it means the maximum power point tracking. So I will have two objectives. Okay, and besides the maximum power tracking, I need to limit the output. For instance, if I have high wind speeds, I need to limit the active power. Okay, so the control system of the wind turbine comprises these two cross-coupled controllers. This is cross-coupled controllers. What is the first one? Is the pitch angle. Okay, so the pitch angle provides the beta reference. Okay, so the pitch angle provides the beta reference. This is the pitch angle. Okay. Yeah, I will have here the beta reference to the pitch drive system. Okay, so I need to move here the small motors. Okay, in order to control the angle of the blades. I will call these two controllers cross coupled controllers. Okay. What about the converter control? In this case, I will have two decoupling. I will have here two decoupling control loops. Okay, so the first one is the pitch angle control. Yeah, I will provide the beta reference. Okay, the second one is the maximum power point tracking system. Okay, in this case, I will provide the active power reference to the generator side converter. So the output is the reference. Okay, this is my first let's say control system, the wind turbine control. Okay, so the summary from these cross-coupled controllers, I will get the beta reference and the active power reference. Okay, for the stator controller. Okay. What is the second control system? In this case, is the converter control. So for the converter control is for decoupling control of the active and reactive power. This is the objective. Decoupling control of the active and reactive power. Do you remember what are the objectives of this one? The first one is the pitch angle control. Okay, and the maximum power point tracking. Okay, this is the two objectives of the wind turbine control system. Okay, for the converter control system, I will have here two objectives too. The first one is the decoupling control of the active and reactive power. Okay. So what about the first power controller? Is used for rectifying. Is used for rectifier. This is my first the machine side converter control system is used for rectifying. Okay. What about the generator side control? The generator side control system works as an inverter in order to convert DC into AC of a fixed frequency. Okay, so I will call this my frequency converter. Okay, I will call my frequency converter. Okay, so this is the control system of the full scale converter wind turbine. Okay, so let's analyze the first case for the squirrel cage induction generator. The control system of the generator in this case is the squirrel cage induction generator for the side converter. So the control system of the generator side converts will be described for a widely use in the first case for the squirrel cage induction generator, and later on we will continue with the permanent magnet synchronous generator system. Okay, for these two topologies, to achieve the control of the active power and reactive power decoupling, okay, of the generator, and obtain a better dynamic performance, okay, so I will have here the control of the generator side converter is generally controlled according to the rotor flux orientation technology. It means the field-oriented control. Okay, so to achieve the decoupling of the active and reactive power, okay, so the generator side converter is generally controlled according to the field-oriented control. So what does it mean? Means the generator rotor flux. Okay, I will have here, this is the D-axis, for instance. And this is the Q-axis. Okay, so it means the generator rotor flux. So let's use another color. Is aligned with the D-axis of the synchronous rotating reference frame. In other words, the rotor flux on D-axis is equal to the magnitude of the rotor flux. What about the Q-axis? If I am using the field-oriented control, okay, the rotor flux on Q-axis is equal to 0. Okay, is equal to 0. So let's analyze the following. Okay, so from the previous lecture, we know the following equation. This is from the previous lecture. We have already demonstrated this equation. I will have here the stator voltage on D-axis is equal to the stator resistance times the stator current on D-axis. Okay, plus I will have here the derivative of the flux, the stator flux on D-axis with respect to the time, okay, minus the synchronous speed times the stator flux on Q-axis, okay. This is the D component. What about the Q component? Okay, so I will have here the stator voltage on Q-axis. So we have already demonstrated this equation in the previous lecture. Okay, so I will have here the stator resistance times the stator current on Q-axis. Okay, plus I will take the derivative of the stator flux on Q-axis with respect to the time. Okay, plus the synchronous speed times the stator voltage on the axis. This is the equation for the stator. What about the rotor? For the rotor, I will have here the rotor voltage on the axis, okay, is equal to the rotor resistance times the rotor current on the axis, plus I will take the derivative of the rotor flux on the axis with respect to the time. Okay, so I will have here minus the synchronous speed times the rotor flux on Q-axis, and this is equal to 0 because I am working with the squirrel cage induction generator. Okay, and the last equation for the rotor is equal to, I will have here the rotor resistance times the rotor current on Q-axis. Okay, plus I will have here the derivative of the rotor flux on Q-axis with respect to the time. okay, plus the synchronous speed times, okay, so I will have here the rotor flux on the axis, okay, and this is equal to 0, once again, because I am working with a squirrel cage induction generator, okay? So these are the 4 equations for the voltages. What about the fluxes? Okay, what about the fluxes? So I will continue with the fluxes. Let's call this equation number 1. Let's call this equation number 2, 3, and 4. This is for the voltages, okay? What about the fluxes? Okay, so what about the fluxes? Okay, so let's clear this part. Okay, so from the previous lecture, we have already demonstrated the equation for the fluxes, okay? So let's call this equation number 5. Okay, so let's call this equation number 5. And this equation is for the stator flux on the axis. So the stator flux on the axis is equal to the stator inductance times the stator current on the axis, okay? Plus the magnetizing inductance times the magnetizing inductance Okay, I don't know what is going on with this computer today. Okay, so once again. Okay, so I will have here the stator inductance times the stator current on the axis plus, okay, I will have the magnetizing inductance times, I will have here the rotor current on the axis. I will call this equation number 5. What about equation number 6? This is the Q component, okay? This is the Q component. I think it's better off to use Active Spire. So let's open Active Spire. Okay, so meanwhile, let's continue. Okay, so let's call this equation number 6. Let's call this equation number 6. So the next component is the Q component. So we will have here the stator flux on Q axis. Let's call this equation number 6. Okay, we have already demonstrated this equation in the previous lecture. Okay, so I will have here the stator inductance times the stator current on Q axis. Okay, plus the magnetizing inductance times the rotor current on Q axis. This is equation number 6. Okay, so let's call this equation number 7. Equation number 7 is about the rotor fluxes, okay, on DQ axis. So I will have equation number 7. This is the rotor flux on the axis, okay, is equal to the rotor inductance times the rotor current on the axis plus the magnetizing inductance times the stator current on the axis. And the last equation is equation 8. This is the dynamical model of the squirrel cage induction generator. Okay, so I will have here the rotor flux on Q axis is equal to the rotor inductance times the rotor current on Q axis plus the magnetizing inductance times the stator current on Q-axis. Okay, so if I am working with a flux orientation technology, with the rotor flux orientation technology, we say in this case the rotor flux on the D-axis is equal to the magnitude of the rotor flux, okay? And the rotor flux on Q-axis is equal to 0. Therefore, in equation number A, this flux is equal to 0. Okay, this flux is equal to 0. So from this equation, isolating the rotor current on Q-axis, because I am working with the field-oriented control, but in this case, it is the rotor flux orientation technology, okay? So I will have here the rotor current on Q-axis is equal to, isolating from this equation, I will get the magnetizing inductance over the rotor inductance, okay, times the stator current on Q-axis. Okay, times the stator current on Q-axis. So let's work in the first equation. Okay, this is my first equation, the stator voltage. I will copy this equation. Okay, let's work in the first equation. I will copy here my first equation. And this is the stator voltage on the axis, okay, is equal to, this is the stator resistance times the stator current on the axis, okay, plus taking the derivative of the stator flux on the axis with respect to the time. This is equation number 1, minus the speed times the stator flux on Q-axis. Okay, so I will work in my first equation. Okay, so first of all, substituting equation A into equation 6. Substituting equation A. What is the equation A? Is the rotor current on Q-axis. So substituting equation A into equation 6, I will get the stator flux on the Q-axis. Yeah, I will substitute this current into this equation. Okay, so substituting equation A into 6, I will get the stator flux on Q-axis, okay, is equal to the stator current times the stator inductance times the stator current on Q-axis, okay, minus, I will have here the magnetizing inductance square over the rotor inductance times the stator current on Q-axis, okay? So this is equal to taking out the common factor, the stator current on Q-axis. So I will say the stator flux on Q-axis is equal to, so I will taking out the stator current on Q-axis times the stator inductance. I will have here times 1 minus, I will have here the magnetizing inductance square over the rotor inductance times the stator inductance. So do you remember this term? This is the leakage factor, right? This is the leakage factor, or the leakage coefficient. Okay, the leakage factor or leakage coefficient. So I will get substituting, I will get the stator current on Q-axis times the stator inductance times the leakage coefficient. Okay, times the leakage coefficient. Okay. Okay, so I will call this equation, the equation X. Let's call this equation X. Okay. So equation X substituting into equation 1. Okay, substituting this term, okay, I will get the stator voltage, the stator voltage on the axis. Substituting this in the first equation is equal to, I will have here the stator resistance times the stator current on the axis, okay, plus I will take the derivative Okay, I will have here the stator voltage on the axis minus, I will have here the speed times the leakage coefficient times the stator inductance times the stator current on Q axis. Okay, I will call this equation I. Okay, I will call this equation I. So now I want to work with equation 7 and equation 5. So substituting equation 7 into equation 5. Okay, so let's back. I will have here equation 7. This is equation 7. I will substitute this equation into equation 5. Okay, so equation 7 into equation 5. Okay, I will get the stator flux on the axis, okay, is equal to the stator inductance times the stator current on the axis plus the magnetizing inductance times, I will have here the rotor flux on the axis over the rotor inductance minus the magnetizing inductance over the rotor inductance times the stator current on the axis, okay? And this is the current, and this is the current, the rotor current on the axis, okay? So continue the demonstration. I will have here the stator flux on the axis, okay, is equal to, I will have here the stator inductance minus the magnetizing inductance squared over, I will have here the rotor inductance times the stator current on the axis plus the magnetizing inductance, I will have here times the rotor flux on the axis over the rotor inductance, okay, over the rotor inductance. Okay, so taking out the stator inductance of this term, taking out, so I will have here the stator inductance, this becomes 1, okay, minus, this is the magnetizing inductance over the stator inductance times the rotor inductance, okay, times the stator current on the axis plus the magnetizing inductance times the rotor flux on the axis over the rotor inductance. So once again, do you remember this is the leakage coefficient, okay? Okay, so I will have here the stator flux on the axis, okay, is equal to the stator inductance times, this is the leakage coefficient, times the stator current on the axis plus I will have the magnetizing inductance over the rotor inductance times the rotor flux on the axis. Okay, so let's call this equation C. Okay, so substituting equation C into equation Y, okay, I will get the stator voltage on the axis, okay, is equal to the stator resistance times the stator current on the axis plus, okay, so substituting, I will have here the derivative. Okay, so substituting, I will have here the stator inductance. This is the leakage coefficient times the stator current on the axis. Okay, plus the magnetizing inductance over the rotor inductance times the rotor flux on the axis with respect to the time. Okay, minus, I will get the speed times the leakage coefficient times the stator inductance times the stator current on Q axis. Okay, take the stator current on Q axis. So taking the derivative, I will get my first final equation. Okay, so my first final equation is the stator voltage on the axis is equal to the stator resistance times the stator current on the axis plus the leakage coefficient times the stator inductance, taking the derivative of the stator current on the axis with respect to the time, okay? Plus, I will have here the magnetizing inductance over the rotor inductance. I will have the derivative, okay? With respect to the time, minus the speed times the leakage coefficient times the stator inductance times the stator current on Q-axis. Okay, and this is my first equation. Okay, and this is my first equation. So now I want to work on the second equation. Okay, what is my second equation? Once again, I will copy here. The second equation is the stator voltage on Q-axis, okay, is equal to the stator resistance times the stator current on Q-axis, okay, plus the derivative of the flux. This is the stator flux on Q-axis, okay, with respect to the time. This is equation 2, okay, this is equation 2, plus the speed times the stator flux on the axis. So substituting equation X into equation 2, okay, I will get the stator voltage on Q-axis is equal to, I will have here the stator resistance times the stator current on Q-axis plus the derivative. Okay, so substituting, I will have here the leakage coefficient times the stator inductance times the stator current on Q-axis with respect to the time. Okay, plus I will have here the speed times the rotor flux on the axis. Okay, the rotor flux on the axis. So taking out of the derivative, so I will have here the stator voltage on Q-axis, taking out the leakage coefficient of the derivative, taking out. So I will have here the stator resistance, okay, times the stator current on Q-axis, plus the leakage coefficient, taking out of the derivative, okay, times the stator inductance, times the derivative of the stator current on Q-axis with respect to the time, okay, plus the speed times, okay, in this case, this is the stator, okay, on the axis, and this is D, okay. So finally substituting equation C into equation L, okay, I will get the equation for the stator flux in Q-axis, okay. So in order to have the two equations on the same page, okay, so I will clear now. I will have my second equation, okay, so I will get my second equation. Okay, so this is the stator flux on Q-axis, okay, is equal to the stator resistance, the stator current on Q-axis, plus the leakage coefficient times the stator inductance times the derivative of the stator current on Q-axis, okay, plus times, I will have here the leakage coefficient times the stator inductance times the stator current plus the magnetizing inductance over the rotor inductance times the rotor flux on the axis. Okay, so pay attention to these two equations. Okay, I will get the decoupled items of the stator voltage. What are the decoupled items? Is this one. This is my first term. This is decoupled. Okay. And this term is decoupled. Okay. It means I have the decoupled items of the stator voltage. In order to carry out the control of the active and reactive power, okay, in a decoupled way. Okay. So I will have here, this is my first term, and this is my second term. So pay attention. I will have here the stator current on Q axis. I will have here the stator current on D axis. So normally, in order to control the reactive power, okay, and the reactive power and the active power, okay, I will use for this the stator current on the quadrature axis, and for the active power, the stator voltage on the axis. We are demonstrating here the decoupled control. Okay, we are demonstrating the decoupled control. Okay, so for this case, okay, so let's continue. Okay, so the conclusions. I will have here the given value of the rotor flux on D axis is usually set at the red value. Okay, and the actual value of this flux is equal to the magnetizing inductance in order to have the control diagram. Okay, the block diagram in order to carry out the control. This flux, the rotor flux on the axis, normally is equal to the magnetizing inductance over 1 plus, I will have here the time constant, this is tau, okay, times the stator current on the axis, okay? This is for the flux, okay? What about the electromagnetic torque? So from the previous lecture, we have already demonstrated the electromagnetic torque is equal to 3/2, okay, times the number of poles times the magnetizing inductance over the rotor inductance times the rotor flux on D axis, okay, times the stator current on Q axis minus the rotor flux on Q axis times the stator current on D axis. Okay, because I am working with a field-oriented technology, we know the rotor flux on D axis is equal to 0. Okay, so I will put this term into the torque equations. So I will say this is equal to 0. Therefore, the electromagnetic torque, okay, is equal to, I will have 3/2. I will have here the number of poles. This is the magnetizing inductance over the rotor inductance times the rotor flux on D axis times the stator current on Q axis. Okay, so pay attention, the electromagnetic torque is controlled only by the stator current on Q axis. Okay, so the conclusion is the reactive power and the electromagnetic torque is controlled by the stator current on the axis. Okay, on the other hand, the rotor flux angle, I will have here the rotor flux angle can be computed with the following equation, the integral of, I will have here the rotor speed plus the stator speed. Tell me. Go ahead, Mr. Shawa.
The flux rotary in the axis is 0 because the magnetic torque is negative.
No. The reason is I am working with a field-oriented control theory. Okay, I am working with a field-oriented control theory. It means, let's suppose I will have here the D axis, and this is the Q axis. Okay, so once again, the generator side converter is generally controlled according to the rotor flux orientation technology. Okay, it means I will have here the rotor flux is aligned with the d-axis. Okay, it means the rotor flux on the d-axis is equal to the rotor flux because this is linked with the d-axis. So what about this component? This component is equal to 0 because I have only one component, and this is the component on the d-axis. So this is the reason the rotor flux on the q-axis is equal to 0 for the field-oriented control theory. In this case, according to the rotor flux orientation technology. Is that clear, Mr. Jawa?
Yes, doctor. The question is the flux, the rotor flux is the Q axis, no the.
Okay, this is the axis.
Yes.
Okay. And the
This
q-axis is 0.
Okay.
Right. Yeah, is that clear?
Yes, doctor.
Okay. Okay, so let's continue. So we are working once again in the rotor flux orientation technology. That is the reason it's possible to carry out these simplifications, okay? Okay, so finally, I will say how to compute the synchronous speed. Okay, normally, in order to compute the synchronous speed, okay, so in order to compute the synchronous speed, this is equal to, this is an approximation, the magnetizing inductance times the stator current on q-axis. Okay, this is the time constant times the rotor flux on the axis. So I will take these two equations. Okay, I will take these two equations in order to plot the block diagram. Okay, in order to have the block diagram. Okay, so let's continue with this. So this is the block diagram of the generator side inverter control. Okay, so do you remember my first equation? My first equation is about the rotor flux on the axis. My second equation is about the electromagnetic torque. So I want to have here, for instance, this is the rotor flux on the axis, okay, is equal to the magnetizing inductance over, I will have here 1 plus, this is the time constant, times P, times this on the axis. Okay, so once again, the output is equal to the input times the transfer function. Okay, so I have here the output, I will have here the input, I will have here the transfer function. Okay, this is my first question in order to have the block diagram of the generator side inverter control. Okay, on the other hand, I will have here the electromagnetic torque. Okay, so I will say the electromagnetic torque from the previous equation is this one, right? So is equal to 3/2. Okay, this is the number of poles times the magnetizing inductance over the rotor inductance times the rotor flux on the axis times the stator current on q axis. Okay, so pay attention. In this case, the rotor flux on the axis is equal to the rotor flux. Okay, so pay attention to this constant. Okay, this constant is equal to, so I will have here this constant, okay, is equal to, I will have 3 times the rotor inductance over 2 times the number of poles times the magnetizing inductance. Okay, in order to build this formula. Okay, in order to build this formula. On the other hand, I will have here this voltage, right? So do you remember these two voltages? Okay, these voltages are the decoupled control on active and reactive power. Okay, so do you remember from the previous demonstration we get this is my first term, okay, and this is the decoupled control of the active and reactive power. This is for the reactive power, and this is for the active power. Okay, so I will have